All right. Good afternoon, and welcome to this week's Iowa Learning Farms Conservation webinar. I'm Matt Helmers. Excited to be back hosting today. Especially excited to be hosting for a former colleague at Iowa State, now at the University of Wisconsin-Madison, Dr. Stephen Hall. Dr. Hall is an assistant professor and extension specialist there, and Hariom Yadav is a PhD candidate at the University of Wisconsin-Madison. They're going to talk to us today about the underappreciated role of soil organic matter in protecting water quality. These Iowa Learning Farms webinars are brought to you by the Iowa Learning Farms and also the Leopold Center for Sustainable Agriculture, the Iowa Nutrient Research Center, and Iowa Department of Agriculture and Land Stewardship, and Iowa DNR. I even remembered those even without seeing the slide. Yes, I'm not, I'm still okay. Um, and as always, if you have questions, please type those in the chat box and we'll get those to the speakers at the end. With that, nobody tuned in to listen to me talk, so I'm going to turn it over to Dr. Hall.
All right. Well, thanks so much, Matt, for the opportunity to share some of our work here from a unique long-term cropping systems trial we have in South Central Wisconsin. So I'd like to acknowledge the other co-authors involved in this project, Greg Sanford, who is another faculty here at UW-Madison, Adam Von Hayden, a research scientist, and of course, Randy Jackson as well, a longtime PI of this experiment that we'll talk about today. So I think one of the overall motivating questions for this work is to get a better handle on where and how much nitrogen is lost from our Midwestern croplands, right? You might think that this is a well agreed upon sort of a metric, but I think there's surprising contention out there in the scientific community about sort of what the dominant sources are of the nitrogen loss to our waterways and how these have varied over space and time. And sort of to provide a little bit of context, this is a nice figure from a paper a few years ago by Cheng and colleagues who calculated what they called a nitrogen surplus. So essentially, they took the agronomic nitrogen inputs to agricultural systems. They subtracted back the nitrogen that was removed in harvested crops, and they came up with these numbers. And so what you'll notice in sort of our region of the upper Midwest, there's a lot of this kind of red and orange color. This is indicating a nitrogen surplus on the order of 50 kilograms of N per hectare or more, right? So this is nitrogen potentially available for loss either as leach nitrate or nitrogen gas emissions. But I think it's really, interesting to sort of look among different studies that have taken various aspects of this approach and come up with, pretty different conclusions. So here's a paper published about the same time by Roy and colleagues, again, calculating this nitrogen balance, so the difference between estimated nitrogen inputs and removal in the crop. And what you'll notice, right, there's, right off the bat, you see a pretty different distribution of color across this map, but also these absolute values of nitrogen balance can be quite different due to, differences in assumptions that are made and the underlying data that are used to calculate the values. I throw in yet another study and we get a different answer. So this is a few years earlier from David and colleagues, again, showing that the same sort of geographic region, but very different absolute values in terms of this partial nitrogen balance. So what I want you to focus on are these yellow counties where the estimated nitrogen surplus is on the order of -5 to about 20 kilograms of N per hectare. So estimating much smaller values across the region. And again, sort of the data that you need for this exercise are difficult to obtain, right? We're having to take average values over space and make a lot of sort of simplifying assumptions. And so the question remains, well, what is actually more appropriate for sort of the typical cropping systems in our region? Another really interesting aspect of these studies is that, sort of by definition, they are assuming no systematic change of nitrogen storage in soil organic matter. However, as we know, soil organic matter is typically the largest stock of nitrogen in our agricultural system. So relatively small increases or decreases in nitrogen storage can have potentially high leverage on the amount of nitrogen that's available for loss. So that was one question we really wanted to tackle in this current work. Of course, it's a challenge, right? Because, there frequently don't have robust data comparing soil nitrogen storage over time in a way that's rigorous enough to be able to make sort of general conclusions. Okay, so again, the key questions of our talk, we wanted to address sort of the magnitude of a long-term surplus or deficit of nitrogen across contrasting grain and forage cropping systems represent of our region. And this is useful because if we get a handle on these variables that are relatively easy to measure, things like our agronomic nitrogen inputs and our nitrogen removal in crops, this gives us a fighting chance at estimating these nitrogen transfers that are much harder to measure empirically. So either nitrate leaching or nitrogen gas emissions. And we were also interested, again, as I mentioned, in getting a better sense of the influence of soil change in impacting these nitrogen budgets, right? The relative importance of gains or losses in soil organic matter as compared with sort of the more direct agronomic nitrogen management. Okay, and so again, to do this, we're just relying on simple conservation of mass, right? Um, any difference between inputs or outputs of nitrogen to these systems have to be matched by a change of storage. In terms of the outputs from the system, right, we've got either crop removal or some other form of nitrogen losses to the environment. And so what this means is we could just rearrange this equation, move environmental losses by itself and calculate as the difference or, inputs minus crop removal minus the change in storage to get at these long-term environmental nitrogen losses. And again, we can do this provided that we have sufficiently robust data for the systems that we're studying. And so we have this unique opportunity here in Wisconsin to leverage this long-term cropping systems trial known as WIXT. This is located just sort of northeast of Madison. This was started back in 1989 by Josh Posner. The current PIs of the experiment are Greg and Randy, who are involved in our study here. And WIXT is interesting because it has six, greatly differing cropping systems, ranging on the one end from continuous corn with just synthetic fertilizer year over year, all the way to rotationally grazed pastures where heifers are brought out to graze in the summer. And so this is a really nicely designed experiment where each phase of each rotation is replicated within each of 4 blocks. The plots are big enough that conventional farm equipment can be used, or again, what was sort of more typical back in the late 1980s. And the soils at WIXT are mollisol, so relatively high organic carbon and nitrogen content here. And we're able to leverage the fact that they took really detailed soil samples back in 1989, which were then able to compare with samples that were collected more recently. Okay, enough from me. I'm going to hand it over to Hariom to talk a little bit more about these cropping systems and what we found in terms of our nitrogen balances.
Well, thank you, Stephen, and good afternoon, everybody. So I'm going to talk about the approach and the result of this work. Building on what Stephen just talked about, so we measured a partial nitrogen balance of 6 cropping systems. And these cropping systems can be grouped into 2 groups, cash grain systems and forage livestock systems. So the cash grain cropping systems include continuous maize soybean, and maize soybean wheat system, which has red clover as a cover crop. The forage livestock systems include maize followed by 3 years of alfalfa, maize followed by 2 years of alfalfa, and managed intensive rotational grazing systems. The management of these cropping systems changed over time and was informed by agronomic performance and discussion with farmers, UW extension agents and UW extension nutrient guidelines. And each plot of these cropping systems was managed as an independent field over the long term. Now, to calculate the nitrogen surplus or nitrogen deficit of these cropping systems, we measured three important components. The first one is agronomic nitrogen inputs, which include biological nitrogen fixation, manure, and synthetic fertilizer. And the second one is crop nitrogen removal, which includes nitrogen in grain, silage in hay, and animal biomass gain. And the third important component was change in soil nitrogen, which is mostly ignored in the calculation of nitrogen surplus or nitrogen deficit in cropping systems. So we also accounted for the change in soil nitrogen in our calculation of environmental nitrogen loss. So now we used measured nitrogen in manure and synthetic fertilizer in our calculation. However, for biological nitrogen fixation, we estimated biological nitrogen fixation as a function of yield. For instance, in soybean, we estimated biological nitrogen fixation as a function of grain yield, where we applied linear regression, quantile regression to estimate the different levels of biological nitrogen fixation. So we used 25th quantile to estimate lower rate of nitrogen fixation, 75th percentile to estimate the higher rate of biological nitrogen fixation, and linear regression to estimate the best rate of nitrogen fixation in soybean, as well as in other legumes, in alfalfa and in red clover. And we use two different data sets, one by Dr. Siamperi and colleagues, and another by Dr. Cordova and colleagues. And we compared the different estimates of biological nitrogen fixation between these data sets. And we found that the estimates were relatively similar between these data sets. So we used mean estimate of biological nitrogen fixation in our calculations. And now we also used measured nitrogen in grain, silage and hay, and animal biomass gain in our estimation. And for the change in soil nitrogen data, we used soil nitrogen stock of 1989 and 2019, and the values of soil nitrogen was corrected for changes in bulk density using equivalent soil mass. And we used the soil nitrogen stock of top 0 to 60 centimeter soil profile in our calculation. Now going back to what Stephen discussed about is that there is substantial disagreement in the distribution and magnitude of nitrogen surplus. So now how does our partial nitrogen balance calculation looks like? So partial nitrogen balance, again, just to reiterate, partial nitrogen balance accounts for agronomic nitrogen inputs and crop nitrogen removal. It does not account for soil nitrogen change for now. So we observed fairly good partial nitrogen balance where the nitrogen balance was approximately balanced in cropping systems. We can see some high values as well as some low values. The high values goes up to 26 kilograms per hectare per year, and the lowest value is minus 15 kilograms per hectare per year. However, most of these cropping systems are relatively balanced. We observed a positive partial nitrogen balance in continuous maize, which is about 22 kilograms per hectare per year. The mean nitrogen input in this cropping system is 165 kilograms per hectare per year, and this is the average over 30 years period. The higher values were greater than 220 kilograms per hectare per year. So we applied 165 kilograms per hectare per year on average over this 30 years period, and we were able to remove only 143 kilograms per hectare per year. So the net nitrogen surplus in continuous maize was found to be 22 kilograms per hectare per year. The same way, we found a positive nitrogen balance in rotational grazing systems. However, we think that some of this nitrogen surplus is because of uncertainty in nitrogen fixation estimate from red clover. So the major source of nitrogen input in rotational grazing is red clover, and we are estimating that. So we think that some of this surplus is because of the uncertainty in and fixation estimate. We also observed positive nitrogen balance. However, the magnitude of nitrogen surplus was lower in maize alfalfa systems compared to continuous maize and rotational grazing systems. So for example, we observed 12 kilograms per hectare per year of nitrogen surplus in maize, followed by 3 years of alfalfa, despite of adding 271 kilograms per hectare per year of nitrogen in this system. We also observed some lower values, some negative partial nitrogen balance in these cropping systems, and this is because of the alfalfa phases, where we are removing more nitrogen in alfalfa biomass than being fixed through biological nitrogen fixation. However, in cropping systems with soybean, we observed overall negative nitrogen balances. For example, in maize soybean system, we observed negative 7 kilograms per hectare per year of negative partial nitrogen balance. In this system, the nitrogen is removed in maize and soybean grain, which is higher than the amount of nitrogen being added in this system. The mean nitrogen input in this system is 159 kilograms per hectare per year, but we are removing around 166 kilograms per hectare per year in maize grain and in soybean grains. As a result, we are observing negative nitrogen balance in maize soybean systems. And similar is the case for maize soybean wheat system, where we are removing more nitrogen than being added in the system. However, now, when we compare our partial nitrogen balance with the already published data, we found that our data are more consistent with the figure on the right, which is Dr. David and colleagues' calculation of nitrogen surplus and nitrogen deficits. So now we have discussed about the partial nitrogen balance, which accounts for agronomic nitrogen input and nitrogen removal in grain, silage, and hay. Now, how does our soil nitrogen change data looks like? So this is the change in soil nitrogen data, which is calculated using soil nitrogen stock in 2019 and soil nitrogen stock in 1989. And the soil nitrogen stock is corrected for the changes in bulk density over time. So we observed that the cropping systems with soybean had the highest decrease in soil nitrogen, and the values were greater than 100 kilograms per hectare per year. And in both systems, in both maize soybean and maize soybean wheat systems. However, in cropping systems with alfalfa, we observed a moderate decrease in soil nitrogen, which is greater than 50 kilograms per hectare per year. And this value is 50% less than the cropping systems with soybean. Now, and when we explored the change in soil nitrogen in continuous maize, we found that around 15 kilograms of nitrogen per hectare per year was lost from these cropping systems. However, this value is not different from zero. Now, when we talk about the rotational grazing system, we observed a positive. We observed an increase in soil nitrogen value, which is around 4 kilograms per hectare per year. And this might be due to the incorporation of excess nitrogen into soil organic matter. However, this value was not significantly different from zero. Now that we have discussed about the partial nitrogen balance, where we found that the partial nitrogen balance of our cropping system is approximately balanced, where input and output are approximately equal. And now we just discussed about the change in soil nitrogen, where we observed a greater decrease in nitrogen in maize soybean system, followed by maize alfalfa systems. And now when we combine these two components, and we can calculate environmental nitrogen loss. And this is the amount of nitrogen being lost from these cropping systems over a 30 years period. And what we observed is that the cropping systems with soybean lost the highest amount of nitrogen, and the magnitude was greater than 90 kilograms per hectare per year. And this was followed by maize alfalfa system, which lost between 70 to 80 kilograms nitrogen per hectare per year. The lowest environmental nitrogen loss was observed in rotational grazing system, and we believe that some of these nitrogen might be due to an uncertainty in the calculation of biological nitrogen input from red clover in this system. And now when we compare the relative contribution of environmental nitrogen loss between partial nitrogen balance and soil nitrogen, we can see that most of the environmental nitrogen loss is contributed by soil nitrogen change rather than a partial nitrogen balance. Now, talking about the soil carbon to nitrogen ratio, which represents the chemistry of soil organic matter, when we calculated the carbon to nitrogen ratio of the cropping systems, we observed that the continuous maize had the lowest carbon to nitrogen ratio, which is 10.1, whereas other cropping systems had slightly higher carbon to nitrogen ratio. However, when we calculated the change in carbon to nitrogen ratio, we observed increase in carbon to nitrogen ratio in most cropping systems. However, in continuous maize soybean system, this CN ratio remained consistent over time. And this is consistent with the mining of soil organic matter. As in essence, if we lose nitrogen from soil, the carbon to nitrogen ratio will increase. And we can see that in our data as well, where the carbon to nitrogen ratio is increasing because we are losing more nitrogen compared to carbon from these cropping systems. With that, so now what is the implication of this work? So effective nitrogen management using 4R method is necessary, but insufficient to reduce nitrogen losses from these cropping systems. We also need agricultural practices that can retain or increase soil organic matter. So how does that look like? We can explain that with an example. So assuming a steady state soil organic matter. So in that condition, if we apply 160 kilograms fertilizer nitrogen and remove 130 kilograms nitrogen in grain, the available nitrogen for loss will be 30 kilograms nitrogen. However, but in another condition where the soil organic matter is decreasing, then if we apply 160 kilograms fertilizer nitrogen and remove 130 kilograms nitrogen in grain, the surplus will be 30. And again, the decrease in soil organic matter will contribute by 30 kilograms if the soil organic matter decreases by 0.1%. So there will be in total 60 kilograms nitrogen available for loss if the soil organic matter from a cropping system is decreasing. Now in the third scenario, if the soil organic matter is increasing by 0.1%, then if we apply 160 kilograms fertilizer nitrogen and remove 130 kilograms nitrogen in grain, the partial nitrogen balance will be 30 kilograms nitrogen. And at the same time, if there is increase in soil organic matter by 0.1%, that extra 30 kilograms nitrogen will be assimilated in soil organic matter, and the net nitrogen available for loss will be 0 kilogram nitrogen. So we want this scenario where we want to increase soil organic matter to retain that surplus nitrogen in these cropping systems. With that, I want to again invite Stephen to talk more about the ongoing management at Wixt.
Okay, great. So I guess, this all sort of begs the question, well, what could you actually do in these systems? And I should have mentioned earlier that Arlington is a little bit different from, the situation in north central Iowa in that we don't have tile drainage. So these are relatively well-drained soil. So that's a little bit of context. I think it's important to think about how these cropping systems are managed currently. And so in our conventional continuous maize system, we have chisel tillage, to deal with the residues. In our maize soybean rotation, we still have strip till during the corn phase. In our alfalfa rotations, we have relatively aggressive tillage to kill off the alfalfa prior to corn planting, and we have manure applied, prior to the corn in that phase, and then during the first year of alfalfa. And I think this sort of invites the opportunity to think about evaluating these old practices and potential changes. And so my colleague Greg Sanford has initiated some split split plot designs in these mixed plots, where for the grain systems, they've begun to implement what they're calling ecological intensification practices. So these are sort of shown on the bottom. And so what they're doing is trying to completely eliminate tillage, both from the continuous maize and the maize soybean rotations. In those systems, they're replacing synthetic fertilizer with dairy manure. The idea is, well, if we're adding a little bit of organic matter, what differences could that make to these systems? And also adding cover crops where possible, right? In an effort to increase the carbon inputs to these systems as well as decrease the leakiness to nitrogen losses. We'd love to do a similar sort of experiment with these forage cropping systems as well. I think there's a lot of opportunities for improving the performance of the alfalfa rotations in particular, right? If we could plant corn green into that standing alfalfa and terminate it with an herbicide rather than with intensive tillage, right? Keep the living cover longer. If we could think about shifting the timing of the application of manure, so more of that is actually retained by the crop rather than lost. Also opportunities for thinking about creative application of manure to the grazing lands. I think these are all sorts of things that we might think about, things that we know producers are already doing on the landscape that could address these goals of helping to maintain or increase soil organic matter while also helping to decrease nitrogen losses. So again, overall points. Effective management of fertilizer is necessary, right? That's sort of a precondition to avoiding nitrogen losses. But as we've shown, right, even with fairly careful nitrogen management over 30 years, the soil was really the dominant source of nitrogen losses. And I think, this is one site in the upper Midwest. And so I think it would be really valuable to have more of these opportunities to ground truth the nitrogen dynamics, right? Before we start really making conclusions about what's happening on the Corn Belt. I think it's really important to get all of those details right about the nitrogen budget. So hopefully there's plenty of time for questions, and we look forward to that.
Yep, we will definitely have time for questions. So if we can go to the next couple slides, we'll get.
Oop. And I'm sorry, I forgot acknowledgments here. All of the folks that funded the Wix trial over the many decades and all of the people that worked up this fantastic data set that we were able to walk into, current support from USDA. And here are the CEU credits.
Yeah. So yeah, definitely. It's important to acknowledge those that came before us to get some of these long-term studies started, right? I feel the same way with some of my work. So, all right, if you watch this webinar live and are wanting to earn a CCA CEU, please email Elena Whitaker, ALENAW at iastate.edu by 5 o'clock today. Include your name, the name you entered to watch the webinar, and your CCA number. Again, ALENAW at iastate.edu. Go to the next slide. And if you are willing to fill out a voluntary demographic survey, we'd greatly appreciate it. Only one survey response is needed for 2026 webinars. You can scan that QR code or go to iowalearningfarms.org/survey. Next slide should be plug for actually our Beyond the Basics Advanced Cover Crop series starts next week. Mark Licht and I are going to do that. So no formal presentation, but we're going to have dialogue and take questions that come in on the chat box. So we're going to try to talk a little more about cover crops and thinking toward the future on cover crops. This will be part of a series that we have, and we have a number of speakers lined up, a number of participants lined up for this season. And I think we have maybe a couple more slides here. One is this webinar and all our webinars are archived and available on the Iowa Learning Farms website, or we have a specific Iowa Learning Farms webinars YouTube channel. So go watch to your heart's content. There are many good ones. And then I think a last slide to put a plug in for tomorrow. This is going to be a real treat, I think. Carl Kurtz, that has 50 plus years of experience in prairie restoration, is going to share some information on establishment and management of prairie. think there's some video from this summer. So as we're getting through the winter, it'll be nice to look on some prairie video for last summer. So please consider joining us tomorrow at 1 p.m. Central Time. And you can find information on that on the Iowa Learning Farms website. Okay, we got some questions here. Can you talk a little bit more about the environmental loss? I think both gas and leaching emission losses, and maybe even which one you think might be a more dominant pathway.
That's great. And I'll actually turn it over to Hariom. Some of his
Okay.
other chapters are actually involving explicit measurements of leaching. So that
Okay.
story's coming along.
Yes, so I'll go back to this slide where I'm talking about these environmental nitrogen losses. So we have so on the top panel, we have partial nitrogen balance, which accounts for the inputs and outputs, and at the bottom, we have environmental nitrogen losses.
I think the question is it lost as a gas or through
Yeah.
leaching?
Okay, so this environmental nitrogen loss is the total nitrogen losses. We cannot total nitrogen losses in the form of nitrogen gases and nitrogen leaching. So we cannot separate from between emission losses and leaching losses based on the data we have. Some of these losses might be in the form of gases, and most of these losses is in the form of nitrogen leaching. But in my in my thesis, I am also calculating the nitrogen leaching losses from these cropping systems, and I am observing the similar kind of trend in my data as well.
Yeah, and just to add, I sort of the magnitude of the leaching losses we've observed over the last, since we started is sort of in the ballpark of, 70 kilograms per hectare. So high losses. That similar work at Arlington done a couple of decades prior found similar kinds of value. So, on the high end for what you would see in many Iowa watersheds.
Yeah.
But there is high nitrate groundwater in the area around Arlington. Yeah,
Yeah.
great question.
Is there, I guess, any info on the manure being added? Is it liquid or pen packed with bedding?
So yeah, we are applying liquid manure in maize alfalfa systems, and also we are applying composted poultry manure in corn, soybean, wheat systems.
Okay.
Wheat system, yeah.
Okay.
Thank you.
Can you go to your soil end stock slide? Somebody asked about the y-axis was given as a rate. They were just wondering if that was correct or whether it was changes in end stocks.
No, that's the rate. So that's the change in stock over, divided by 30 to put it on you an annualized
Annual basis. Okay.
Yep.
Yeah. Do you think the presence of tile drainage within your study site would impact the accumulation of in-field soil organic matter?
Yeah, that's a very, very interesting question. I think we, can't really speculate since these are well-drained soils, but it would be very interesting to have access to the same kind of, chronosequence of soil carbon and nitrogen in a tile-drained system. I know some folks down in Illinois have done those kinds of studies and suggested, well, maybe things have achieved steady state, but I think it's really an open question where we might be, losing or potentially gaining soil nitrogen across the region.
Yeah, on your site, you might not see a very little impact of tile drainage because you might not get much because it might just leach right below the tile lines if it's a well-drained soil, very deep.
And that's one thing that makes it harder to actually measure nitrate leaching explicitly, right? We have to go to lysimeters rather than just the tile drain plots. So
yeah. Somebody asked, many of our dairy farms are transitioning to corn or to grain, corn and soybeans. How do we avoid organic matter losses in systems that don't have manure? We aren't seeing an increase in organic matter from continuous no-till corn, grain, soybean systems with cereal rye cover crops planted after soybean harvest. Any suggestions?
Well, and I would say maybe the jury is still out, right? It's just really hard to measure these changes over time, and you have to. The statistical challenges are really substantial, and so I think, it's possible that we may be able to gain back some organic matter with some of these systems. And indeed, if you look out in the literature, there's evidence that can happen, although, it's slow and difficult to document. But
Yep.
agreed that those land use, transitions from dairy systems to grain systems do pose a real change to the
Yep.
system.
Um, how sensitive are the budgets to the assumptions of the N fixation rates?
Do you want to tackle that?
Yep. So we compared the mean estimate of different levels of biological nitrogen fixation, and we found relatively similar values between these estimates of biological nitrogen fixation. With that, I would also like to mention that in maize alfalfa systems, some of the estimates were the mean estimate was like a little bit off from the higher and lower estimate, but based on the available data, that is what we can present. Yeah.
And just to add to that, I think that's great. I think the alfalfa system definitely was the most sensitive to differences in
Okay.
assumptions. And we could, depending on if you were assuming a higher or a lower end fixation rate, you could shift that quite dramatically. And I think that is one of the biggest unknowns. But we think that average value is pretty much right because we're adding, a fair amount of manure to these systems, which is going to suppress fixation probably early during alfalfa. And then later
Okay.
on, right, we might get some pretty darn high rates.
Okay.
We'd love to do some isotope work to really dive into that. However, the overall story doesn't really change. The dominant lever is still the soil nitrogen change, as opposed to those subtle differences in the partial nitrogen
Okay.
balance.
Is it safe to assume that much of the soil N was remaining from the prairie? And if so, how much longer can those rates of soil N loss continue?
And so this is a really interesting question that folks have debated. And so this site has been under agriculture for 150 years. And so it was in a long-term similar cropping systems, alfalfa rotations prior to the experiment. And so, this could still be the legacy of prairie carbon, but if so, it is a very long tail. And so we'd love to do some more radiocarbon work to actually look at how old that carbon is that's
Okay.
being lost.
Oh, what was the composition of the rotationally grazed paddocks, kind of percent grass, percent legumes?
So the assumption was that around 35% of the total biomass is red clover in the rotational grazing systems. However, we were not able to achieve that biomass in the rotational grazing, so we were like fertilizing the system to get that biomass in the rotational grazing. Yeah, so the answer is around 35% of the total biomass.
And then
is
the
being
balance was the cool season grasses.
Yeah.
So yeah.
Okay. A couple folks, I don't think with this one you looked at it, but maybe any other studies about, Stephen, measured that input and output of nitrogen in the soil when using a winter rye cover crop.
Sort of the long-term soil
Yeah,
N
I
implications
think
of
so.
a winter rye. That's a great point. So a number of studies, right, have looked at the carbon change implications,
Yeah.
but a lot of those studies, they just don't report the nitrogen. And I think, it's methodologically, typically when they're measuring carbon, they're also measuring nitrogen. However, it's less sensitive because it's a smaller quantity. And so I think that's really a call to the researchers out there to look at your nitrogen data sets and see what we can put together.
Okay. Let's see here. I think. Okay. In non-mollisol soils that are more weathered, would you say there is more of an urgency to increase soil organic matter to decrease nitrogen losses, like in soils in the Southwest that are more weathered?
Mm. Well, I think just by definition, you don't have, the same risk of loss, right? You don't have that stock event to lose. Whether it will actually be possible to achieve substantial gains, I think is an open question. Sort of an extreme end here, when you're thinking about like sandy soils in the Midwest, just very difficult to increase organic matter regardless what you do. So there are some sort of inherent constraints of soil properties and perhaps climate involved there.
Okay. Somebody asked if you have any insight on loss rates during the 30-year study period. Was it linear or kind of proportional loss per year?
So it differed among cropping systems. For example, um, so we estimated the cumulative partial nitrogen balance, but we didn't estimate the cumulative environmental nitrogen losses.
Mhm.
We observed that the cumulative partial nitrogen balance of some of our cropping system was like monotonic, which decreased at a constant rate. So, but we didn't estimate the linearity of the environmental nitrogen losses of these cropping systems.
We just had access to these two time
Yeah.
points for the nitrogen. There was another soil sampling in 2009 that Greg did for his PhD, so we could try to track down those samples and get a hold of the nitrogen data. For the agronomic side, there are some really interesting temporal trends in some of the
Okay.
systems following sort of shifts in management. So the organic corn, soybean, wheat system was really having some what I understand was having some yield difficulties, and so they started adding composted poultry manure in like 2008, and there we see really
Okay.
different trends following that management shift. I think for the like continuous corn, the fertilizer inputs were quite low for a while, and they started ramping those up and started seeing big gains in production, but also I think greater nitrogen surplus in some of the later years. So there is some interesting nuance there with some of the agronomic trends. Unfortunately, we don't have the resolution with the soils really to be able to parse it out. However, one thing that sticks with me if you just look at the carbon, the continuous corn has done some interesting things over time and maybe shifting directions. That's my recollection. And so we would expect sort of nitrogen to roughly track with that.
Okay. Um, I guess, why do you think organic matter's been neglected so much in the conversation, and how do you think we can turn people's focus to the issue of retaining and increasing organic matter to fix nitrogen loss?
I think it's hard to measure, right? It's just to get a signal that you can, right? Because we have all these great experiments where we can compare treatments at the same time, and that's great, but then we can potentially miss these long-term differences. So.
Yeah. All right. I think that gets at most of the questions, and in the interest of time, I think we'll stop there. I want to, again, if somebody needs a CCA CEU, please email Elena Whitaker, ALENAW at iastate.edu by 5 o'clock today, including your name, the name you entered to watch the webinar, and your CCA number. Please tune in next week. Mark Licht and I will talk cover crops, and consider tuning in tomorrow to hear from Carl Kurtz talk about 50 years of prairie restoration. Hariom and Stephen, thank you so much for a thought-provoking webinar today. It's really important, and I'm going to amplify one more time that these long-term studies are so very important. I think we sometimes think about changing treatments quick, but it's only in some of these long-term studies can we get at some of these long-term processes in the soil. So I know for me personally, it gave me a lot of things to think about. Students that work for me may not be happy because I think we need to do some sampling at Gilmore City where we have 15, 20 years of cover crops or forage or no-till. So Stephen, give you and Hariom last word.
Well, thanks. We just want to thank everyone else that we're standing on the shoulders of giants here, the folks that started and maintained the trial. So thanks for having us.
All right. Thanks so much.